So, welcome back to our video lectures on projective geometry. In our last lectures, we intensively talked about Cayley Klein geometries. We learned about measurements, about fundamental objects, about transformations in these geometries. And this time we want to see Cayley Klein geometries at work by looking at theorems from elementary geometry and see how they generalize to general Cayley Klein geometries. A disclaimer at the beginning: in the perspectives book there are about 70 pages about that subject, and here I only will scratch the surface of what's going on. I will do some kind of cherry picking and highlight somehow the most important parts of the story. So, what kind of theorems are we going to talk about? Well, we will take really typical theorems from elementary geometry, and the most typical theorems there are triangle theorems. So things like the altitudes in a triangle meet in a point. So you take 3 points forming a triangle, you look at those lines that are perpendicular to one of the sides and go through the opposite point. And if you consider all 3 such lines, you will find out that they always will meet in a point. We will see that this has a generalization in Cayley Klein geometries with some interesting twists. We will see that in a moment. Second theorem we want to look at is the angle bisectors of a triangle meet in a point. This time we look at those lines that go through one of the triangle points here that bisect the angle. So the angle between the side and this line and this line and this side here should be exactly the same. And if we draw all these 3 lines, we will find out that also these 3 lines will meet in a point. There are other theorems like the medians meet in a point, the perpendicular bisectors meet in a point. We will talk a little about these theorems. So one of the first questions here is how to define concepts like being perpendicular and being the angle bisector in a general Cayley Klein geometry. For instance, the measurement may be a hyperbolic angle measurement, and the question is, what does orthogonality mean in such a case? And the idea what we will do is, well, we take the essence of the definition of orthogonality from an elliptic angle measurement and derive a formula, actually several formulas and geometric constructions for orthogonals that also apply in the general case. So let's talk about orthogonality first. So we want to characterize when 2 lines in a Cayley Klein geometry are orthogonal. So the question is, when should L be called orthogonal to M? And well, in the Euclidean case, you would say you have a 180-degree angle here, and it's orthogonal when the angle of L to M is exactly 90 degrees, half of 180 degrees. But you can rephrase it in a way that is more general. You can say, well, it is orthogonal if the angle from M to L is exactly the same as the angle of L to M. So it's a kind of midpoint statement for angles. It's like having a midpoint of 2 points for distance measurement corresponds to having a perpendicular for angle measurement. So how would we characterize that by formulas? So let's look. We want to say that the angle of LM equals the angle of ML. And if we measure that angle in a Cayley Klein geometry, what we have to do is we have to take the point of intersection, take the 2 tangents to the fundamental object. We usually call them x and y, and then we have to take the logarithm of the cross ratio of these 4 lines, multiply it by the constant, and compare these magnitudes. Since multiplying by the constant and taking the logarithm are just functions, we can immediately say, well, we will have this condition if the cross ratio of the two expressions is the same. So the cross ratio xy_lm should be the same as xy_ml, and usually I will assume that L is not equal to M and X is not equal to Y, so we might make also sure that this cross ratio is not the one. So, but this completely characterizes the situation, because we know about cross ratio. If we interchange two elements in one of the pairs, it just becomes its own reciprocal. So we are asking for a number not equal to 1 with the property that it is its own reciprocal, and there is only one such number, which is the -1, which means that geometrically these lines here are in an harmonic position. So you get a completely geometric characterization of orthogonality in the following way. Take the two lines, take their intersection, draw the tangents to the fundamental conic, and if those four lines are in a harmonic position, then the original two lines were orthogonal with respect to that Cayley Klein geometry. And this can be used as a definition for orthogonality in general Cayley Klein geometries. And there is a nice fact relating this definition here directly to the algebra of the homogeneous coordinates of the objects involved. So what you can actually prove is the following. If your fundamental object is again represented by a primal dual pair A and B, where B is the dual matrix here, then two lines are orthogonal if and only if this equation here holds. So you take the homogeneous coordinates of M, multiply them by the dual fundamental object, multiply by L, and if this is 0, then the two lines are orthogonal. In my book, The Perspectives on Projective Geometry, you find a general proof for that works in all Cayley Klein geometries. We will not do that proof here because it would be quite a detour to get the very general statement. Instead, I want to convince you for the case of real non-degenerate fundamental objects that you end up with this kind of formula, and if you want the details for the general case, please read in the book. So what we are doing is a kind of mix of algebra and geometry and a kind of step-by-step construction that needs a little bit reading in the pictures. So perhaps it will be the most complicated part of this video lecture of today. So let us start with our fundamental conic. And well, we assume that it is given by a primal dual pair A and B, and we have a line that we call L. And now we want to characterize when a line M really is orthogonal to that line. And for that, let me first look at this red expression that we had here, which was B times L. B times L has a geometric interpretation. B times L is the polar of that line with respect to our fundamental conic. So if you draw the two tangents at these 2 points, they will intersect in a point, I call it L star, which is exactly calculated as B times L. We already had that in one of the earlier lectures. So, and now what we claim here is that if we have a line M that passes through that polar, because this is exactly what I've written down here, then we will have a right angle between those two lines. Well, admittedly, it does not look like a right angle at all, but that's okay, because we are in a general Cayley Klein geometry and we cannot expect that right angles look like Euclidean right angles. We will encounter some special cases where this happens, but not in that picture. So what we have to do is to check that the situation around that point of intersection really satisfies our characterization of orthogonality, meaning that LM, X and Y are in harmonic position directly at that point. So let's draw this point of intersection, and let's also draw the two tangents. So these two tangents now are my x and y, and I have to prove that if I did this construction here, then actually these four lines here are in a harmonic position. And now you have to be a little bit tricky to see that this is indeed the case, and we have to refer to several statements that we had before. So first thing, let's take this point here and draw the polar of that point. So the polar of that point is the line that you get when you well, take the two tangents. This was our x and y, take their intersection with a fundamental object and draw the polar. And now you see some interesting thing happening in the drawing. This polar automatically passes through our point L star here, because this is a geometric theorem. Actually, we proved that theorem earlier by the following fact. We at some point considered 4 points on a conic and calculated the cross ratio of those 4 points on a conic. So we calculated this cross ratio with respect to our fundamental object in that case, and we found out that these 4 points are in harmonic position if the following happens. If you draw the tangents from 2 of the points and take their intersection, it will exactly meet the join of the other 2 points. And since this relation is symmetric and we constructed this line here in a way such that the line L passes through this point here, and we got these points A and B here. We get from this relation here that A, B, C, D are harmonic, which implies that the white line goes through that point. So we now know several things. We know, well, it passes through that point, and considered as points on the conic, these 4 points are in a harmonic position. Now we have to take this harmonic relation and turn it into a relation about the 4 lines that we have, and again we have to read in the picture. So next thing we do is we look at those 4 points that we have here, and if you look at those 4 points, it turns out that they are also in a harmonic position, and we can see that essentially immediately by observing that well, our 4 points here were in a harmonic position. And now observe what happens if you view these points from point D. Let me draw 2 more lines into that picture. If you view these 4 points from point D, then you get the following lines. So you get the tangent at point D to our point L star, and yet you get the other 3 connecting lines. And we know that they are in harmonic position. These 4 lines are in harmonic position because we had a harmonic position of the 4 points here. So this implies that our 4 points here are in harmonic position. But now look, our 4 lines that we have here really are the joints of this point, the white point here, and the 4 points, which means that our 4 lines are also in harmonic position, which finally proves that L and M are indeed in an orthogonal position. I know this was a tough one, but see what we've proved. We've proved that we get a construction for orthogonality by simply constructing the pole of my line L with respect to the fundamental conic, and any line through that pole will be perpendicular to the line L. And on the other hand, we got this algebraic characterization that we have here, which can be read just by the calculations that lead to the pole L. So this characterization is exactly the algebraic one that we wrote here. So let me have another look at that. I could have approached that from a completely different angle, no pun intended. So assume our fundamental conic is a circle, and look what happens if you measure orthogonality of two lines that meet in a center. So if you have the center of the circle and you calculate the pole of that line, what happens is that you will get a point that is infinitely far away in the direction orthogonal to the line L, and this time I mean Euclidean orthogonal. So any line M that you have that passes through that pole, which means it's a Euclidean perpendicular to your line L, finally will be an orthogonal according to our construction. In other words, if your fundamental object is indeed a circle and your two lines intersect in the center of that circle, you can check perpendicularity of these two lines simply by looking at the Euclidean angle at that point, and essentially we just proved that by our construction. But actually there is even a deeper reason for that, because in this situation where you have a circular fundamental object and you measure in the center of that object, the hyperbolic perpendicular is the same as the Euclidean perpendicular, but this does not only hold for perpendicularity, this holds for any angle. So hyperbolic angle measurement in the center of a unit circle as fundamental object is the same as Euclidean measurement. So if you just have two lines that meet in the center, just measure your good old Euclidean angle and you get the hyperbolic angle. And the reason for that is the following. If you take this point P here and consider its polar with respect to the fundamental object, what you get is the line at infinity. So it's a line passing also through our point that we had here as the intersection of the two tangents. But then the following happens. So how do you measure the hyperbolic angle at that point? Well, you have to take that point, and from that point you have to draw tangents to your fundamental objects. They will be complex in that case, but taking the tangents means taking the joints to the intersection of this line with the fundamental object. But this is a line at infinity, and this is a circle, and the intersection of the line at infinity and a circle is just the points I and j. So on that line here, you somehow have I and j, and the tangents through point P will be exactly lines through I and j. So in our formula, what you really get is the Euclidean distance measurement. Take the cross ratio of your two lines L and M with respect to I and j, and this proves that Euclidean measurement in the center of a circle is finally the same as Euclidean measurement. Let us, as a next step, take this characterization and look what happens in different Cayley Klein geometries. So assume that we have convinced ourselves that perpendicularity is actually the same as this equation, then for hyperbolic geometry we proved it's exactly this construction. If you have a line and you want to have a perpendicular to that line, what you have to do is to say, well, I construct or calculate the polar of that line with respect to the fundamental object, and any line through that point will be perpendicular to our line L. So here the fundamental object in the standard way of representing a real non-degenerate conic would be this matrix here, where we have the unit circle here. Let's see what happens in the elliptic case. In the elliptic case, this -1 down here turns into a +1, and we learned that it is the best thing to view the elliptic case on a sphere. So we scale down the homogeneous coordinates of our objects to the unit sphere, and so points are again antipodal pairs of points on the unit sphere, and lines correspond to great circles on the unit sphere. So actually in this embedding, if we take a line and the corresponding vector that represents it, it's exactly the vector that points to the pole of that line, because in that case our matrix is just the unit matrix. So multiplying the homogeneous coordinates of L by the unit matrix just gives the coordinates of the vector that represents the line. So there is no change here. Again, the elliptic case in a sense is the simplest one, and again all the lines through that pole will turn out to be orthogonal, and here you see one example. And if you switch on your 3D imagination, you will see that if you have an equator and a north pole in a sphere, that every great circle through the north pole will be automatically orthogonal at the equator. So also here we get a nice definition. How about Euclidean geometry? In this Euclidean geometry, we have our line, and our fundamental object this time has a 0 here in that spot. So if we multiply b times L, what we get is the first coordinates and a 0 in the last spot, which means we get a point at infinity that points in a direction orthogonal to L, which is exactly what we want to get, because if we have a line M through that point at infinity here, then we will get orthogonality here as we expect. And you can play this game for other Cayley Klein geometries as well. I leave it to you as an exercise, either for doing or for reading in the book. Here is one more remark about interesting special cases. So for instance, tangents to the fundamental objects are self-orthogonal. So for instance, in this picture here, this line here, if you consider the pole of that line, it's this point of intersection here. Let me just draw a new example. So let's take a tangent here, and the pole of this tangent is this point here, which tells you that this line goes through its own pole, which means it's orthogonal to itself. This means such counterintuitive things like lines being perpendicular to themselves may happen in Cayley Klein geometries. Second remark, if you look at Euclidean geometry and you apply this definition here, it turns out that the line at infinity will be orthogonal to any other line, because if you plug it into that formula, then b times L gives something with a 0 in the last spot, and line at infinity has coordinates 0, 0, 1, which will always have a 0 product with the pole. So you should consider the line at infinity being orthogonal to any other line in the Euclidean plane, which is something that we usually don't encounter if we talk about Euclidean geometry. Okay, let's now come to the theorem that the altitudes in a triangle meet in a point. Let me first convince you of this theorem by just doing the construction. So here I have a fundamental object. I draw a triangle, and now I construct the polars of the three lines that we have in that triangle by simply taking, well, the polar point of these lines. So you take the line and the fundamental conic, and this here is the polar point, and this here is the polar point, and this here is the polar point. And now I construct the perpendiculars, which means I have to connect each of the triangle corners to the corresponding polar point, which I do now. And if you look at that, you see even in that case, it looks as if the altitudes in a triangle really meet in a point, and this is a pretty stable thing. So even if I start to move around my points, if you observe this point of intersection here, this is well, seems to be true. So now let's prove this statement, and the proof will be a little algebraic detour. So I've drawn the picture you just saw, and I labeled some of the points. So my points are P1, P2, P3. My lines are L1, L2, L3, where the label is in the following way. L1 is the line opposite to P1, L3 is the line opposite to P3, and so on. And here I have the corresponding poles of the lines, which are BL1 up to BL3. And then I claim that these altitudes here, H1, H2, and H3, that they meet in a point. For the proof I'm doing, you know that you often need some kind of non-degeneracy conditions to make things that not fall apart. I assume that P1, P2, P3 are indeed not collinear, and that the poles that I get here are not degenerate, so they are not the zero vector. Actually, it happens that the statement is more general than the proof for this special case under those non-degeneracy assumptions, but this proof is reasonably tame. So let's start with the lines. So the lines here have some homogeneous coordinates, and you can get the corners of the triangle by simply forming the meet of the lines. And this works because we assumed that P1, P2, P3 are not collinear, so the lines do not coincide, so I can really calculate the points from the lines. So I want to join this point, say P1, to the corresponding altitude. So I want to calculate P1 cross product or vector product with BL1. And well, if I insert this expression for P1 here, it's L2 cross L3, I get L2 cross L3 cross BL1, and again I can perform this calculation because I assumed that BLI was not a degenerate situation. I can do that for all three altitudes and get these expressions here. So now look at this formula here, and perhaps you remember some of the Grassmann identities for dealing with vector products. You can rewrite this expression in terms of scalar products in the following way. So you can rewrite H1 is L2 cross L3 cross BL1 in the following way. Take the inner product, the scalar product of L2 BL1 times L3 and subtract this other expression here. If you don't believe that, you can pretty easily prove that, because you see that H1 is in the span of L2 and L3, which means that H1 must pass through the point of intersection here, and the factors here are exactly such that it passes through BL1. You can do that for the other altitudes as well. Now, what do you have to check? You have to check that these three altitudes here meet in a point, which means check if the determinant of these three altitudes really turns out to be 0. Okay, now it gets lengthy. So take the determinant of these three altitudes and plug in the expressions that you get here. And you see, well, you get a really, really long formula. Fortunately, this formula really collapses almost completely, because if you look here, you have L3, L2, L1, L3, L2, and L1 as factors, and if you apply multilinearity, you can look what can combine to what without getting 0. So if you want to factor out, and you look at that term here, it's a multiple of L3, so it cannot be combined with another multiple of L3 without getting 0. So the only term with which it can be paired in the second column is this one here, this one that involves the L1. But this one again cannot be combined with everything in the third column. The only candidate that gets not 0 is this one. And in a really similar way, you see that these three terms here are the only ones that can be combined with each other. So if you cancel out everything that gets 0, you are left with this term. This is the blue one, and this term here, which is the green one. And now you have two, well, pretty plain determinants here with in each column factor times vector, factor times vector, factor times vector, and you can put the factors in front of the expression, and what you get is this here. And what you see here, that this obviously has to be 0. For what reason? Well, first of all, the factors in front are the same. Perhaps you don't see it immediately, but they are the same. So you have, for instance, L1 times BL3, and here you have L3 times BL1. But if you rewrite the inner product in terms of matrices, you see that this term equals this one, that this term here equals this one, and that this term here equals this one. So you can cancel out the factors, then you are left with the determinants here, but these two determinants are essentially the same. It's just a cyclic rotation of the letters, which proves our theorem. Okay, I assume if you proved the altitude theorem in school, it looked way simpler than what we did here. But what we did here is way more general. It proves the altitudes meet in a point theorem in any Cayley Klein geometry under these non-degeneracy assumptions, and you will find many interesting special cases of the theorem in different Cayley Klein geometries. So the altitudes meet in a point is way more general, and it looks like, if you just look at it from a Euclidean perspective, it holds essentially in all the Cayley Klein geometries as long as these non-degeneracy conditions are satisfied. So let me turn to another topic, angle bisectors, and this time I want to be a little more brief and less algebraic. So let's again look at the situation at the center of a circular fundamental object, where we know that the angle measurement here is the same as Euclidean angle measurement. So how would we construct angle bisectors here? Well, one way would be draw all the tangents that you see in that picture and connect opposite points of that rhombus. Then you will get an angle bisector here, and a second angle bisector in a perpendicular direction also here. So important fact, there are always two angle bisectors. So let's take a second copy of that and move it a little bit. And before I move it, I have to explain one thing. What we did here was a completely projective construction. It only involved projective terms like tangents, intersections, and joints. So we constructed these angle bisectors in a completely projective way, which means that if we have a situation where the lines do not meet in the center, we still can apply exactly the same construction and get the two angle bisectors. Again, disclaimer, in general situations, these things will not look like angle bisectors because we don't have Euclidean geometry. We have a general Cayley Klein geometry. So now let's take this characterization of angle bisectors and look at the following theorems. The angle bisectors of a triangle meet in a point. And here's a picture. And what you see here is the following. I've drawn these 3 points that form my triangles. I've drawn these tangents that I need to construct the angle bisectors, and I get those points and I have to connect them. So for instance, if you look at this line here and this line here, I said take these two tangents and these two tangents here and take their point of intersection, connect them, and you will get an angle bisector here, same here and same here, and it turns out that these angle bisectors meet in a point. Actually, I've drawn only half of the angle bisectors. You remember in these directions here, you will also get some angle bisectors. And if you do the construction, actually, it turns out that they will also meet in points. But you see, I'm not able to draw straight lines here. So let's simply erase them again. But why is this true? And the reason for this is really surprising. If you look at this picture and stare for it a little while, you notice, well, it's a theorem about these 3 yellow lines meeting in a point, and they only depend on those 6 points, which only depend on 6 tangents, and we had that before. This is exactly Briancham's theorem. So Briancham's theorem really proves that in Cayley Klein geometries where things are suitably non-degenerate, the angle bisectors will meet in a point. This is a surprising relation of classical incidence theorem like Briancham's theorem to a theorem of elementary geometry like the bisector theorem. And if you read everything in reverse order, you can even use the bisector theorem to prove Briancham's theorem, depending on which you start with. Okay, one more theorem. Let's talk about medians, and this time I only want to show the picture. So the medians of a triangle meet in a point. So again, here is a situation in Cayley Klein geometry where the fundamental object is real and non-degenerate. So what are the medians? The medians are those lines that you get if you take the midpoints of your triangle sides. So be careful, these midpoints here don't look like midpoints, but they are midpoints in the Cayley Klein geometry defined by that object. And if you take those midpoints and connect them to the opposite triangle vertex, they will meet in a point. I won't prove that here because in a sense it's dual to the angle bisectors statement. But I want to point your attention to something else which is very interesting here. So you see, I've drawn those midpoints here, but again, this is only part of the truth. So the real truth is that there are also other 3 midpoints of those points. Okay, you may say, well, this point here doesn't look at all like a midpoint of the 2 yellow points here. But what is a midpoint? It's a point that has the same distance to both of those points. And it turns out, if you do the calculation, that this green point that I've drawn here is exactly at the position where the Cayley Klein distance from here to here equals the Cayley Klein distance from the green point to the other yellow point. And so I have a second midpoint at each of the triangle sides. And actually it turns out that if I draw the corresponding lines here, so these are essentially the second median of each of those triangle sides, then I get those 3 lines, and again I get 3 more points of intersection. And if you look at this theorem, it turns out it's really just the dual of the angle bisectors theorem. Remark on that here, there is a nice Euclidean fragment of this here. Let us do the same theorem in Euclidean geometry. So you have 3 points that form a triangle and you draw the median. So now you are in Euclidean geometry. Midpoints really look like midpoints, and you know, well, they meet in a point. You perhaps proved that in school. But now here we had these second midpoints. What are these second midpoints? And it turns out, if you do these calculations, that these points are the infinite points on the triangle sides. So if you intersect the triangle side with the line at infinity, you will get a second line that is at the same distance from the 2 yellow points. And actually this makes sense because it's simply infinitely far away from both of those points. So, and what happens now if you draw these alternate medians here? If you draw the second median to this triangle side here, you have to draw a line through this triangle vertex which is parallel to this triangle side. And if you do that for all 3 sides, you will recognize that again you get the other points of intersections here, which are in a sense also intersections of medians of the triangle. As a matter of fact, you could even use them to construct the midpoint here, but I won't go into detail here. Okay, let me finish here with a few important differences. So we saw that many things are similar in Euclidean, hyperbolic and elliptic and other Cayley Klein geometries. I want to point out to a few important differences that will become important later, and here is perhaps one of the most notable ones. In hyperbolic geometry, there are such strange things like pentagons that have right angles everywhere. And if you learned everything about orthogonality, you see that this picture here really is already the proof of the existence of such beasts. So you have this side here, and I construct the polar of that by drawing these 2 tangents, and any line through that polar here is a perpendicular to that line. So you have 2 right angles here, and I did that around the entire pentagon, and you get right angles everywhere. So in this kind of geometry, in this hyperbolic geometry, there are such things that do not exist in Euclidean geometry, because in Euclidean geometry the sum of the angles in pentagon is constant and more than 5 times 90 degrees. But on the downside, in hyperbolic geometry, there are no rectangles. So there is nothing like in the Euclidean case, a situation where you have 4 lines such that the angle between the 4 consecutive pairs of lines is always 90 degrees. You cannot do that in hyperbolic geometry. I don't show you why this is the case. Just believe me, this is directly related to this fact here. And this brings us into the fascinating differences between these geometries. And this is what we want to look at in our next lectures. We will have a really deeper look at what is called hyperbolic geometry. See you there.